Hi. So Monday's class was a little crazy with the Zoom and things coming in and out and not working very well. So I thought what I'd do is just do a sort of a quick review of what we did on Monday. And so you'll be able to look this over if you want to, um, just to have it right exactly what was done in that class. And then I'm going to start in class today. Today is Wednesday, September 2nd, and I'm going to start in class today, just sort of pick up where we left off on Monday, but at least you'll have this review if you were confused about what I was talking about on Monday, because the Zoom not working kind of disturbed the flow going in and out. So what I'm going to do is share my screen and go into OneNote and, um, and get a new page. Okay. So I was really talking about the second law of thermodynamics, and this has to do with total entropy. And basically, the second law says that total entropy increases for any spontaneous process. Let me do something here. Okay, so basically any process that happens on its own must be accompanied by a change in total entropy that's positive. Okay, so on Monday, I talked about how this law will help chemists answer a few questions. And the first question I was talking about is, will reactions react spontaneously? That's something that we talk about a lot in this class. Two, how far will the reaction go? Okay, and I believe I talked about how this is, how far the reaction goes is related to, what is the equilibrium constant and how is it related to all of this entropy stuff. So, or all of this, free energy stuff. Okay, so we addressed, no, and then question 3, this is what I'll talk about on Wednesday, on September 2nd. Okay, talk about how will the equilibrium change when conditions change. And by conditions, I mean number of moles of the reactants and products. Another thing is temperature. And then also the pressure. So these are things that I'll address somewhat on Wednesday. Okay, so I'm just talking about 1 and 2 now to give you a little review. So here's the reaction that I was focused on Monday. I could have written this in advance, but I didn't. All right, and so what I had you do was look at this reaction and asked you, does the entropy of the system increase in this reaction? And you could see that there are several reasons why the delta S for this reaction, which is really for the system, and notice I put no subscript. I'm not going to put cis ever. If you don't see the subscript, it means it's for the system. So delta S for the system would be positive. And the evidence for that is, first of all, here you have solids. These are very ordered crystals, ordered crystalline compounds. And on this side, you've made 2 moles of a gas. And gas molecules have much more disorder. We'll learn later that it has a lot to do with their ability to disperse heat with their movement. Okay, so moles of gas Whenever you have more moles of gas on the right side of an equation, you will have a positive delta S by and large. It's like a rule of thumb. Another thing is that the H2O, you're generating liquid from all solids, and aqueous, even aqueous is more disordered. These are all more disordered on the product side. So there's no arguing the fact that the entropy change, the delta S for this reaction, is positive, okay? So we know that. Does that mean, does this guarantee spontaneity? And the answer to that is actually no, because it's not just the system entropy that matters, it's the total entropy. And the total entropy, you know, I'm not sure I recorded this. I'll just take a look. How do I do that? I'm obviously recording. Okay, good. All right, because the total entropy is equal to the system entropy plus the entropy change to the surroundings. All right, that's like everything else. So when we actually ran the video of this reaction, so there was a little beaker here, and this had the two solids in it, and the teacher was stirring this up, and she had a little watch glass under it, and in the watch glass she put a few drops of water, liquid water, okay, and then the reaction happens, and in the end it gets very kind of liquidy, and the watch glass now has ice. So the water froze, and we also were able to monitor, she was able to monitor the temperature, and the temperature drops a lot. So that means that this reaction takes in a lot of heat from the surroundings. So if I were going to try to draw that schematically, I would draw here Q. Q basically represents heat, and heat flows into the system. So that's an endothermic reaction, okay? Now, if heat is flowing into the system, that's going to make the surroundings colder. And what happened was the ice froze. So clearly, there was an increase in order, right? Clearly, there was a decrease in disorder in the surroundings. So the reason for putting water there is because the water changing to ice makes that obvious. It makes it obvious that delta S surroundings is actually negative, okay? But even if the water didn't freeze, even if the water just cooled, cooling means things are moving less rapidly, you know, you have more ordering, slowing. Heat is not able to be dissipated as well. Okay, and in fact, I believe I said that it is, oops. Oh, I don't know what happened. So that, did something happen bad? Doesn't matter. It is always true that when delta H is positive, so you have heat flow in this direction here into the system, delta S SIR will be negative. Okay, that's always going to be true. So what about looking at the delta S total again for this reaction? So we know it's delta S plus delta S surroundings. Okay, now we've already determined that this is positive. That's positive based on the fact that we're generating moles of gas, we're generating liquids and aqueous things from very ordered solids. So delta S is positive, and I've argued that delta S surroundings is negative, and that's because we have an endothermic reaction. So a lot of times chemists will call this, they say that there are two competing terms in delta S total, okay? But we know what the sign of delta S total was, because we know that the reaction went forward vigorously. So that means that we did generate entropy. A total entropy change was positive. So we know that this is positive. So what does that mean? So what can we conclude from that? Well, we can conclude that the magnitude of delta S must be greater than the magnitude of delta S surroundings, because delta S is the one that's positive, okay? And what I did is I showed you this equation. And I said, when we look at this equation, we've also come to the conclusion that there are two competing terms, because you know that delta G negative means the reaction is spontaneous. And so we know that delta G is negative because of our observations that the reaction occurred vigorously. But we know that delta H is positive because the reaction is taking in heat. And we know that disorder increases, which makes the delta S positive, but then this entire term is negative. So again, we have two competing terms. Okay? And whenever you have two competing terms in the delta S equation, this one, you will have two competing terms in the delta G equation. And the reason is that these two equations are very, very closely related. They're actually the same if you manipulate them a little bit. So if we take this delta G is delta H minus T delta S, and I just divide by negative temperature. Okay, so here you can see that these will cancel and you'll end up with a positive sign, and this term becomes just the delta S. This one is minus delta H over T, and this is minus delta G over T, okay? And actually, this is delta S surroundings. We'll learn later. This, of course, is delta S, and this is the total change in entropy. So these are really very much the same. They both come from the second law. This equation actually has a restriction that temperature has to be constant, but we're not there yet. So that's when I said that we were done with question number 1, okay? And I'm just going to talk about question number 2, and then I'm going to pick up in class with question number 3. Okay, so question 2 was, how far will the reaction go? Okay, so how far will the reaction go? Well, from this discussion, we know that delta S total will increase for something that happens spontaneously. And delta G, actually S total will increase. Delta S total will be positive. Let me write that down. So delta S total will be positive. Delta G will be negative. So S total will increase. S total increases, G decreases in the course of the spontaneous process. So if a reaction is actually happening, then it's spontaneous. It's happening by itself. Let's assume it's happening by itself. So if I were to graph the Gibbs free energy, okay, G, first is what I'm going to call it X, but I call this extent of reaction. So this is basically how far the reaction has gone from all reactants to all products. And this is pretty easy if you just have a reaction. R goes to P, 1-to-1 ratio. When you have all reactants, we say that X is 0. If you have all products, that X is 1. So X kind of goes from 0 to 1. All right, so that's what we call the extent of reaction. Now, I have no idea at this point in the semester what the actual functional form of G versus X will look like, but I do know one thing, and that is that if the reaction is going forward, so if the forward reaction is spontaneous, then G has to drop by the second law. So G is going to go down. Okay, it's going to go down. All right. But what happens is that at some point, G stops. At some point, you get to this point where the Gibbs free energy stops dropping. And to go further would actually increase the G. And this is what we call equilibrium. Okay, at that point, at equilibrium, the derivative of G with respect to the extent of reaction, the slope becomes equal to 0. Okay, and this actually defines equilibrium in thermodynamic terms. Okay, so you might ask the question, well, what if we started with all products? So what if we started over here with all products? Okay, well, if you have all products, the reaction is going to go backward. It can't go forward. It doesn't have any reactants. And so this is what it would look like. It would approach the equilibrium from the other direction until the change in G with extent of reaction equals 0. So if you started with all products, then the reaction would go in reverse to equilibrium. Okay. So, so you might ask yourself the question, does the reaction stop dead? You have reactants going to products, suddenly it stops. No reactants form products, no products form reactants. And that's not actually what happens. So the answer to that question is a really nice big no, okay? Because what we have is what we call a dynamic equilibrium. And in a dynamic equilibrium, we have equal rates of the forward reaction and the back reaction. Okay, now if you remember from general chemistry, where if you have a very simple reaction like this, okay, so you have one reactant forming one product, so just rearrange form something else. Sorry about all those beeps. Every time I get an email, I get a beep on 2 computers. So what is the rate of the forward reaction? Well, it only has one reactant, and this is an elementary reaction. It occurs as written. The rate constant for the forward reaction, I'm going to call K forward. The rate constant for the reverse, I'm going to call K reverse. So I basically have the reactants goes to products with a rate constant K forward. So the rate of that, the rate law, is going to be K times the concentration of reactants. That's what happens if it's as written with just one reactant with a rate constant Kf. So that is the rate of the forward reaction. Now the reverse reaction, products goes to reactants with a rate constant Kr. So the rate of the reverse reaction, again, this is first order in products, so it's Kr, concentration of P. Yeah. So this is the rate of the reverse reaction. So at equilibrium, the rate of the reverse reaction and the rate of the forward reaction are equal. So Kf, concentration of R, equals Kr, concentration of P. Okay, this defines the equilibrium point from a kinetics point of view, where you have equal rates. But notice that if I take and divide both sides by the concentration of reactants and divide both sides by the Kr value, that I have this ratio, and you should recognize this ratio as the equilibrium constant. You would call it Kc in Chem 104, concentration equilibrium constant. And it's the ratio of two constants. These Ks don't change as long as the temperature doesn't change. So if temperature is constant, these rate constants don't change. Okay, so this ratio is the equilibrium constant. That's the concentration of products over the concentration of reactants at equilibrium. And so that tells you the position of the equilibrium. If it's a very big number, it means that products are quite favored. If it's a very small number, it means the reactants are quite favored. And I can't derive it for you now, but by the end of the semester, we're going to derive this relationship between the equilibrium constant, or at least the log of the equilibrium constant, and the standard delta G for a reaction. Okay, and this is really talked about at the end of general chem, but you could see that this makes sense, that if KEQ is greater than 1, then the log of KEQ is going to be positive. This negative sign is going to make the right side of the equation is going to be negative. And so therefore, delta G0 will be negative. Now we know that that favors the products, which is consistent with a negative delta G. If KEQ is less than 1, then the log of KEQ is going to be negative, and the delta G0 will be positive. And these two things go together, okay? A positive delta G and a small value of the equilibrium constant, meaning the reactants are favored. Here, the products are favored. And if you have a very, very large KEQ, then the products are really, really favored. And if you have a very, very, very small one, then the reactants are really favored. So this, it runs the gamut. You can have Ks that are near 1, Ks that are, 10 to the 7th, Ks that are 10 to the negative 6, like acid dissociation constants and things like that. So that's where I was at the end of the class. How far does equilibrium go? KEQ tells you that, but it's related to a thermodynamic quantity, delta G0, which comes about really from the second law. And that's all I have to say for today.